So now, number 5. That's if it's metabolic acidosis. So only applies if you're in metabolic acidosis. We're gonna divide you into anion gap metabolic acidosis or non-anion gap metabolic acidosis. And that's it, very simple. But in the ICU, you can't determine the gap without looking at the albumin, because people have low albumin and stuff like that. It's a little bit different than the ER when somebody comes with DKA, but in general, that's the right way of doing it. So the albumin affects your, it's a negative ion, so it affects your anion gap, and the anion gap is basically the gap between the positive ions that we measure minus the negative ions that we measure. There's some ions that we're not charged, we're neutral. So there's some ions that we don't know, negative, that are flowing around in the blood, like lactate and phosphate and sulfate and all of these things, and we don't count them, and that's why we call them the anion gap. We know its number, so if this gap rises, then we know there's more of those negative ions, we have to look for the source. So that's the whole thing about the anion gap. Some acidosis, metabolic acidosis, are by, happen by accumulation of a new acid, so they have a lot of those gap, things flowing around in the blood, and some metabolic acidosis happen by just losing the bicarb, so that there's no accumulation of anything, it's just you're losing bicarb. So anyway, the way to do it, there's a formula in the book. We're not going to remember the formula, we're going to try to simplify it, but it's exactly the same number. I didn't change anything. You unravel it. So instead of remembering a formula, you remember one number, and the number is 2.5. Can you remember 2.5? You multiply the albumin times 2.5. That will give you the expected gap for this patient, right? The expected gap. So it's not everybody has to have a gap of 12 to 14. No, move away from that way of thinking. Just albumin times 2.5, that'll give you the expected gap for you. So if your albumin is 2, your expected gap is 5. And if you have a gap of 8, that's a anion gap metabolic acidosis. If you decide to do it with the formula and stabilize the expected gap at 12 and change the measured gap based on the albumin, you're gonna go through the formula, the brackets and all of these things, and then come up at the end with the same result, right? But easy to remember it this way. Right, next is if it's anion gap metabolic acidosis, and only if it's that. I see people do it for alkalosis, there's no need to. Pure or mixed. And that's where we do the delta. That's the last step, right? So let's talk about that. So basically, we have a patient with this. Okay, so 72230, right? Bicarb of 4, anion gap of 20, albumin of 2. So if we go through it quickly, this is acidosis. Respiratory and metabolic, they both go down in the same direction, so it's metabolic. I'm not going to do number 3, we're going to go to number 4. Is it compensated or partially compensated? Partially compensated, right? And then we're going to jump here. We said it's metabolic acidosis, so we have to find this anion gap or non-anion gap. So what's the expected gap for this patient? 2 times 2.5, that is 5. That's the expected gap for the patient, right? And then, so now, is it anion gap? Yeah, of course. The anion gap is 20, so it's anion gap metabolic acidosis. Then we're going to go to number 6. And that's where we're going to find out if the anion gap is pure anion gap or there's another disorder with the anion gap. So now we said the expected gap is 5. So let's start. The first thing that you need to do in this, and just the one thing that you need to remember, we're not going to do formulas. There's a formula for it, but we're not going to do it in formulas. Just do it in your brain, like 4th grade elementary school people. So basically, just look at the bicarb. The bicarb is the final product. The gap and the loss of the bicarb and the increase in the whatever, all of these things affect what? Affect the final product is the bicarb. So think about the delta change in bicarb first, and then the delta change in gap after. So the bicarb first. So the first thing you do, the delta change in bicarb. How much change in bicarb? 24, the normal, minus 4, that'll give you 20. And then change in gap, right? 20, the gap is now minus 5, that's the expected gap for those patients, and that's equal 15. Right? So the change of bicarb, that's the way I think about it. Change of bicarb is 20. 15 of it is explained by the change of gap. So what explains this 5?
The non-gap.
A non-gap metabolic acidosis. So this guy has a mixture, it's a mixed disorder, and the mixture is between anion gap metabolic acidosis and non-anion gap metabolic acidosis because it did increase the bicarb change. So are we doing this just so we can spend our free time doing these calculations, or do we benefit from it in patients? So we made a mistake when I was a resident. I didn't know anything about this, and my attending didn't know anything about this, and he was a bicarbophobe, so doesn't like to give bicarb. We had a patient who comes in, old guy, lactate of 10, pH loss in the 7.2s, and acidotic obviously, so it was like kind of tunded and stuff like that. And we resuscitated him using a lot of normal saline, because at that time we were using what? Normal saline. We gave a lot of normal saline, and then the pH stayed at 7.2, but his lactate was, for some reason, 2.5. So obviously, we didn't know anything, so we said intractable acidosis, and we talked to the family, and we made him CMO. That's crazy. That is crazy. Of course, this guy is having what? He's having a change in his percentage of non-gap acidosis. So yesterday, when he had the lactate, right, his anion gap was probably, acidosis was the majority of this bar. And then today, after we resuscitated him, give him so much normal saline that he developed a non-gap metabolic acidosis, and now this gap acidosis is only a small percentage, and the majority is non-gap acidosis, which is non-aminous, and just give him bicarb. It'll be fine, right? The kidney, although we always say the rules of being on call, right? Eat when you can, sleep when you can, and don't mess with the pancreas, and understand that the kidney is smarter than you. I call the kidney is like a wife or a girlfriend. You look at her the wrong way, it fails. It fails forever. It's stored in a hard drive. Anyway, so the point here is that the kidney, although it's very smart, is actually stupid when it comes to bicarb and chloride. If you give so much chloride, the kidney confuses that with bicarb and start losing bicarb. Right? So that's why when you give normal saline, it was 154 milliequivalent chloride. You know, the normal chloride is 110, right? So giving all of that chloride, your kidney is losing bicarb and becoming acidotic. That's why. So that's one situation where this happened. What else? What another situation that we have this mixture?
Just like RTA type stuff.
Yeah, RTA or even acute kidney failure in the ICU. These people, you live with them all this time. You notice that if you want to catch the renal failure before it happens, you see that the bicarb goes down. That's before the creatinine and BUN goes up. Bicarb goes down, you started to lose bicarb. Why? Nobody pays attention. I see some people even reading the whole chemistry without even reading the bicarb. It's not important. But anyway, the bicarb goes down, and then the kidney. So most kidney failures in the ICU acutely present as non-gap acidosis and then become gap acidosis and mixture together. You know, after the BUN rises. So that's that. What else? Another condition? Diarrhea. You have diarrhea, you just lose a lot of bicarb, and then you have more diarrhea, and you're not eating and drinking and blah, blah, blah. Then you start a BUN rises and lactate rises and then become a mixture. Okay, so I'm going to change one number. I'm going to change this number only. So same thing, same gas, everything, and same diagnosis, but the bicarb is 20. Right? So the change of bicarb now is what? Is 4. 24 minus 20, that equal 4. So the difference that's going to make is huge, is that because this is the change of bicarb of 4, but the change of gap is 15, so the gap went all the way to here, okay? But something brought it back and settled at 4. So change your gap window all the way to 15, something brought it back, and the final product is 4. So that means what?
Current metabolic alkalosis.
Yes. So this guy, anion gap metabolic acidosis with metabolic alkalosis, right? What conditions give us that?
Vomiting.
Vomiting. Somebody vomits, loses the hydrochloric acid, alkalosis, and then vomits more and not eating, and BUN and creatinine, BUN and lactate goes up. What else?
Dehydration and stuff.
Dehydration, but I've never, yeah, it can reach that level, at least acutely, but very briefly, because quickly we'll switch to acidosis. You can have contraction alkalosis, but quickly we'll switch to metabolic acidosis right away. What else?
Milk alkali syndrome or something.
Well, but what is the acidosis going to come from? That's alkalosis only. Yeah, so we need something that will give us, the opposite of what you said. DKA patient comes in with metabolic acidosis, anion gap metabolic acidosis, but then vomits intractably. Then, of course, same thing will happen. It will mix, right? What else? COPD patient. It will screw up this equation because his normal number is not 24 on the bicarb. So he looks like he's having alkalosis with the acidosis, right? And he does have alkalosis with the acidosis when you do the equation, right? Or the professor is giving bicarb. If I start giving bicarb to the patients, then of course I'll skew this value. Okay. All right. Well, that brings me to, if I send a gas on one of you guys